that in sp combination there is a s orbital of one atom and p orbital of another atom. So the combination of s orbital of one atom and p orbital of another atom pointing along the axis joining the nuclei. When the lobes overlap, the pores overlap with the same sign, bonding molecular orbital form and the lobes overlap with opposite sign, then antibonding molecular orbital form. MOTs form. So there will be the two conditions again here, and if there is a lobes overlap with the same sign, then bonding molecular orbital form. In that the electron density is very much in between the nuclei. Here also the lobes overlap the opposite sign, then there will be the less electron density. So let's discuss by graphic representation. Now we know that this is an s orbital. Now if you see, this is the same side and this is an opposite side, so this is an anti-bonding MOs and this is an bonding. Bond by sp orbital. This is a formation of bond by sp orbital. All about the sp combination. Now let's discuss what is a pd combinations. Now the combination of p orbital of one atom and d orbital of another atom is known as pd combination. As we know that the p orbital have a dumbbell shape, so here if we see the orbital in dumbbell manner and it will be combined as the d orbital, that is py, that is dxy. In d orbital there will be 5 suborbital, that is dx, dy, dz, dx square minus y square and dxy, dyz, dzx, d square minus y square and dz square. So in that we are going to discuss the dxy orbital with the py orbital of p orbital. Then there that is the sigma bonding molecular orbital. You can write anti-bonding one, that is here we can take so this is a sigma star anti-bonding molecular orbital. Anti-bonding molecular orbital. And this PD combinations in generally take place in carbonyls and cyanides. Cyanides means that there is a PD combination is generally observed in transition metal complexes. Now let's discuss what is a DD combination. Here the combination of d orbital of one atom and d orbital of, so here we can say that the combination of d orbital of one atom and d orbital of another atom is also known as a DD combination, which results in formation of bonding and antibonding molecular orbital. Molecular orbital, that is and delta by combination of and overlap of 2dxy or dx plus y square orbital. Z X Z Y X So this is a DD combination of atomic orbitals. So this is a DD combination of atomic orbitals. Non-bonding combination of orbitals. That is a non-bonding combination of orbitals. Now we know that the combination of atomic orbitals, combination and overlap of atomic orbitals resulting in the formation of bonding and anti-bonding molecular orbitals. In bonding molecular orbital, the energy of this bonding molecular orbital is always less than the anti-bonding molecular orbital. Anti-bonding molecular orbital have a greater energy. So the electron density which is concentrated in between the nuclei of this bonding and anti-bonding molecular orbital, and for the effective overlap of that bonding orbitals, to obtain a bonding molecular orbital, the sign of the lobes must have the same, and for anti-bonding molecular orbital, the sign of the lobes must have they must have a different sign. So from that we can deduce the bonding and anti-bonding molecular orbital with the concentrated electron density in between the nuclei. These are the all cases where there is a formation of non-bonding combination of orbitals. Here there is a s orbital is bonded or non-bonded with this py orbital, that is pz orbital. Here s orbital is bonded with the py, and that is non-bonding molecular orbital, that is non-bonding molecular orbital. Here also, that is p orbital is bonding with the pz atomic orbitals of p, that is px orbital is bonding with this pz, and this is a formation of that non-bonding atomic orbital. Here also there is a formation of px atomic orbital with d orbital, and there is a formation of non-bonding orbital likewise this. So these are the some cases or examples where there is a formation of non-bonding, there is a non-bonding combination of atomic orbitals. So we will stop here. Thank you.